lecture. That's interesting. You see the screen, guys?
Yes.
Awesome. All right, so welcome everybody. And thanks for coming. Let me see, this is the 4th week, right? So we're just right after the midterm and you've got 3 weeks left before the exam, right? I hope everybody is feeling well or feeling better at least. But if you don't, I think you will feel better after today's lecture, because we have a few announcements to make. Let me see why this is not getting forward. All right, so this will be some important announcement. I think probably will be helping for most of you. I was pretty happy when I just saw the, our feedback we had last Tuesday, about how many hours you spend on your exercises and independent learning. But later on, Wenqi informed me that there was a mistake because I excluded this kind of lecture time. So actually, somehow you're spending hours more than you should be, which is not good. I mean, it should be good if you really study the lecture because you're going to get it for your own. But anyway, we want to keep the well-being of the students as well. And that's why I think in the later feedback collection, I saw, many positive kind of signals and also a few negative signals, because many of you are claiming that too much time are needed for the course. Yeah. That's why we also gave you the chance to write a learning, let's say, diary. You just did last week, so thank you for providing that. We didn't read fully, but at least from some of you that this is becoming an issue, and also the computational training is becoming an issue. It has been so in previous times as well. But I thought this year we're doing this teamwork that would be helpful for definitely most of you. But obviously it turned out it's not that efficient yet. So that's why for the following 2 or 3 weeks, let's say 2 weeks, because we didn't plan for the 3rd week anyway. So for the following 2 weeks, we're going to put the computational training to optional or omitted, so that there will be optional. So optional means there will be out from the grading system. You will have the chance to learn it, so they will be provided by kind of Wenqi via videos. So you have the chance to follow and to see at least what is going on and what kind of products you could develop from the computational training. But you don't have to follow it during the exercises, or you also don't need to perform an assignment or computational assignment. Instead, so this will be correlated to the last point. So for the guys who really fell in love with the computational training and operating software, writing codes and all these issues, the 2 case studies are opening this week. So one of them, if you still remember, one of them is computational related, and it will be a very interesting one. So I hope you know, for the guys that love computational work, try to do it, because you will collect extra points that help with your grade. And it's opening this week. So that means you could just transfer your energy to do this for the computational training. But for the assignments, for week 4 to 6, they will be purely based on, let's say, the lectures you have taken and the book you're reading. So it's basically, let's say, less computational exercises. So this is the first point, as well as the third point. And the second point that I would to share with you is we're gonna move the QA session. So it's not Wednesday, right? It's on Tuesday. But anyway, it will be moved to the exercise session on it's also not Friday. So to the exercise session on Thursday. So I don't know if everybody remembers the QA session. So we set that up at the beginning. So just to basically help you, if you have any questions you would like to discuss with the teaching assistants. But it turned out not too many are showing there. So that's why we're gonna move that to the exercise session. So you could have your questions asked during the exercise session in a large, let's say, community. Maybe it's helpful for everybody, because I see very active contribution in the general discussion. So we have a few members are really discussing or contributing there very actively, which is good. And maybe it's more helpful if you just ask in person during the exercises, because everybody will hear some, let's say, problems or solutions concerning their own issues. So this is the second, and the third is already just given. And the 2 case studies are open. So I spoke about basically the first one, and the second one is about literature review. So that will basically try to shape your ability, let's say, finally to write an essay or to write your bachelor thesis or to write your project report that's going to happen right now next year. And so this will be helpful for all of you. So it's a good training, and you will be able to collect extra points out of the second case study as well. And for more details, they will be announced during the exercise session this week. So if you would like to know more details, visit the exercise session this week, and you will also know how the grading system will be looking like. All right, so that's the 3 updates for this week, or let's say for our midterm feedback, basically from you, and we try to make an action concerning that. So hopefully that will make our second half learning experience more interesting, or let's say more focused. Now let's try to get our series contact for basically for this week. So this week we're gonna have something a little bit different, so quite different from previous weeks. But first of all, let's look at what have we done in the previous weeks. So maybe you still remember this diagram. I don't need to repeat it anymore. You're seeing it basically every week, and that really guides you, let's say, technically where you are. Maybe you still remember there's also another diagram I'm not plotting here, but that guides you, let's say, emotionally where you are, right? I hope everybody now is really recovered from the, let's say, the valley of despair, and really getting, you know, up and up to become an expert of material science and engineering. If not, you will be in about 2 to 3 weeks. And speaking about the technical part, you know, we have spent about 1 to 2 weeks on structures, if you still remember. So our first week completely is on structure of materials. Basically, it touches, you know, it started, let's say, from the electronic structure and atomic structure, and finally we arrived at crystal structure, if you still remember those BCC, FCCs. And we made a certain, let's say, connection to properties, but let's say very basic density and the Young's modulus and this stuff. And right after that, in the second week, we already moved to the properties. So because you remember the core about material science is to understand the correlation between structure and the property. Yeah. So we had a systematic, let's say, training about properties. So starting from elasticity and we moved to plasticity. Maybe remember the stress strain curve that we used to learn the material property, and we used to also derive the instability, the Cecilia criterion, to know why there's necking, why there's maximum force or maximum stress when you just pull a material. I think you've learned every stuff about that. And in the third week, we still stayed in material properties, but kind of moving to performance, because we're not just studying one property, so elastic or plastic. We basically studied failure. So failure, you know, the types of failures, so fracture, you know, there's cleavage, there's ductile, and there's transition between ductile to cleavage. You learned, let's say, mechanisms, and you learned also the quantitative measure. So how to basically characterize or predict cleavage at ductile fracture. And then we learned many other types of failure, basically fatigue, creep, and corrosion. So that is gradually becoming a performance, because performance is basically a skill up. So you scale up from your material piece of sample to a structure. And second point about performance is that you are really assembling all the properties together. So you evaluate, oh, this material is having corrosion, at the same time maybe fatigue or creep and so on. So that is basically the performance of your materials or performance of your structure. So that's basically the 3 weeks that we spent together. So you see, it's quite a lot. So we are covering most of the atoms in this tetrahedral. And in the center, maybe remember, this is mainly given during the exercises. So the exercises are really governing all these 3 atoms right here. Starting from this week, so as you can see, there's only one guy left in this tetrahedra. So we're going to basically aim that guy, which is the process. So basically, we're moving from performance to process. So we don't have an error here because the direct connection is not there. But indirect connections are basically everywhere. The processes are important because, you know, finally processes are determining your structure. You know, this is the part about material engineering. We learn all this knowledge. Of course, we're eager to learn knowledge. We want to know why, why things are behaving like they're behaving right now. But we also want to do something. After we know why, we want to just produce things that we want them to behave the way we want, right? So that is the process. So process is the key actually for material engineering. And basically, this is the functionality part about material science engineering. Before we go to processes in detail, so we are not really touching the core or the technologies about processes this week, but we need to basically prepare you. We're going to prepare you in 3, let's say, contents or topics. The first one is about diffusion, and the second one is about phase diagram, and the last one is about phase transformation. Before we already dive into diffusion, I would like to give you a reason why we're doing this. Let me see if we got, all right, cool. We got most of the guys here, awesome. Anyway, let me just try to ask you, if we want to produce something, so we said the process in end is about producing something. If you think about the engineering materials that we have in our daily life, you know, not about a wooden chair or a wooden, let's say, desk, you know, these are nature materials, basically, we consider. Let's say we consider engineering materials in terms of metals. Yeah, imagine your kitchenware, for example, a knife. Yeah, if you just think about how this knife is made, yeah, you probably don't think about how it was made in terms of, you know, the last step. You just bought it from supermarket, right? I'm asking you how this knife is made, basically starting from the earth. And we don't have a knife, let's say, made naturally, right? So it was made by something, yeah, during certain processes. Maybe you think about how it was made. And then it would be able to tell you why we're learning all this stuff. Just for the sake of time, I basically review the answer or review part of the answer. You will have the chance to think about this question again after this week. So then you will have much better vision. And because most of our engineering materials, especially metallic materials, yeah, so steels, aluminum, titanium, and all these engineering materials or structures, you know, they are made through a process called solidification, right? So if you think about it, that we don't have iron directly made from the earth. And iron is somewhat in nature material as well as aluminum, most likely in oxidation form, right? So we have the iron oxidation and we have aluminum and so on. You know, the first process we need to do is to perform reduction, and then you have basically liquid iron also. And then you need to solidify it, and then to basically produce the final product, right? So that is the reason, actually, that is reason we need to learn all these three items, so diffusion, phase diagram, and phase transformation, because there is basically already a phase transformation if we speak about just liquid and solid. But the phase transformation we're speaking about in today's lecture is much more complicated than just from liquid to solid. All right, I think that gives you a kind of an idea what we're doing today. Let's just dive into them one by one. So first we start with diffusion. So why we're starting with diffusion? Because diffusion is the, let's say, the basic of all these phases transformation. So a small introduction about diffusion. First, we would like to ask you, what is diffusion? Think about it. What is diffusion? Maybe it's a very, let's say, easy or common phenomena you're seeing every day, like this picture here. So when you just have a coffee, if you are not a black coffee lover, you would just produce, or you just, you know, put some sugar or milk into the coffee. You don't want the sugar or milk just to stay there, right? As the sugar in a small packet, you want the sugar diffuse into your coffee. That is the kind of process, right? But we will give you a proper definition, and then you understand what diffusion is really about. And second, we will tell you what is the mechanism of diffusion. So that is rather knowledge giving. So we will tell you the mechanism, but we will not give you a, let's say, mathematical derivation about mechanism or so. Because diffusion is a process very much related to thermodynamics. And as far as I know, for most of you, you didn't have the knowledge about thermodynamics yet. So anyway, keep it in mind. When you just learn thermodynamics, keep those questions I will give you during today's lecture, and you try to find an answer about it. And thirdly, we want to know what is diffusion used for. That is the main idea for us to learn it. And the fourth one is when we just are done with all this, let's say, quantitative understanding about diffusion, we want to ask you or give you some definition or description about diffusion in a quantitative way. So this is always how we do it, right? So we move from mechanism to some quantitative description. And finally, we would like to ask you or let you know what is the what factors will influence diffusion. Maybe you know already, yeah. Relate to, again, this phenomenon when you want to dissolve your sugar into your coffee. So when the coffee is hot, it's somewhat easier to diffuse, right? When you have a cold coffee, you probably find difficulty. The sugar will just stay as sugar. They don't dissolve. This is already getting the second part of our lecture today. We will keep that in mind and get it back. So after that, I would like to give you, let's say, what are the learning objectives for our lecture today. So you will see a lot of unknown words. Yeah, basically they're marked as pink. And so if you don't understand them at the moment, don't worry. This is just a kind of a, let's say, an appetizer that you don't really understand. But you will understand it right after this in about 45 minutes or 40 minutes. Let's just go through them. So first learning objective is, after the course, you will be able to name and describe 2 atomic mechanisms of diffusion. Yeah, that's already a keyword about atomic. And the second one is you're able to distinguish between steady state and non-steady state diffusion. And third, you will be able to write the Fick's first and second law in equation form, and you will be able to define all the parameters and know their applicability. Yeah. Don't worry, you will learn all these laws. And the fourth one is you're able to write a solution to the Fick's second law. You will understand why, because the Fick's second law is not a normal equation. It is a differential equation. That's why you will have a solution equation to the Fick's second law for a certain condition. So the condition is the semi-infinite solid. You'll be able to write the solution for the Fick's second law, and then you will be also kind of able to understand all the parameters. The last point is that you could calculate the diffusion coefficient, and most importantly, you know what factors are influencing your diffusion coefficient, which is the temperature. All right, so these are the 5 main terms. Basically, you're going to learn one concept. So let's say 2 mechanisms, and basically 2 laws or 3 laws if we consider the diffusion coefficient equation as a law as well. Let's just go through them one by one. So first of all, what is diffusion? I've already asked about it. Here I'm giving you an animation. So maybe you don't read the text first, you look at this picture. So this picture is basically displaying you a phenomena. You can try to imagine the black points as some gas atoms. Yeah, and initially, so now it's initially you pay attention to here, this point and that point. So initially we had 2 basically atoms right over there. So they're foreign atoms. So they were put into the gas atoms initially. And right after that, you see the curves developing. So these 2 atoms are basically diffusing in your gas atoms. Maybe some of you remember, this is a phenomenon we learned, let's say in high school or junior high school, which is called the Brown motion or Brownian motion. And basically it is telling you, the atoms in gas or liquid form, they're not just staying there as they are, but basically they're moving. You remember that. So they're moving just randomly. And this can be also reviewed if you just, this season, normally we don't have good weather in Finland, but surprisingly this year it's really doing well. So if you just try to see, let's say in an early morning, when you have just a slice of sunshine into your room, it's the best when you just look at a slice of sunshine. And then you can see, following these lines of sunshine, you would be able to review lots of, small particles. Yeah, no matter how clean your room is, you will be able to see them, right? They're basically a dust. So you're able to see those small particles. So the dusks, they're not atoms. Yeah, otherwise you don't see them. So the dust particles are basically these two blue guys. So you see them. What you don't see, yeah, because why they're just floating in the air, they're actually heavier. The density of those particles are heavier, slightly heavier than your gas. Yeah, but why they're floating everywhere, they're not just down to the earth. Basically because they're doing something like this. So because they're diffused in your air because of the Brownian motion of your gas atoms. Yeah, so I think with these two phenomena, and you could list many, so there are really many and many. You probably could really now give a proper definition about diffusion. So diffusion is defined as the mass transport by atomic motion. Yeah, this is the best, let's say, reviewed if we speak about the first, let's say, case when we have the diffusion about gases or about liquids, because you see this random Brownian motion from microscope or so. But if we talk about solid, so I already told you we have solid, let's say, producing engineering materials. We just produce something from liquid to solid, and the solid. So we're speaking about iron, we're speaking about aluminum, but they're never pure iron or pure aluminum, right? There are always some other atoms. Those atoms are diffused into basically your matrix of iron, of aluminum. So what is the diffusion mechanisms when we have solids? Yeah, so it's more or less the same thing. So it's more or less the atoms are moving, but here they're a little bit more specific. I will tell you why. But here you can see for the solids, the two mechanisms are vacancy diffusion and interstitial diffusion. Maybe you still remember what is interstitial. When you speak about FCC, BCC crystal structures, so we will go there. These are the two mechanisms for the solids. So in principle, they are still the same. If you just learn thermodynamics, you will be able to know why they're completely the same. There are two types. If we speak about diffusion of solids, actually this applies to liquids as well. But today, as you know, we're going to speak about solids, because you will learn the liquids and gases during your high school or so. The diffusion we're really specifying in this lecture is mainly about solids. There are two types of diffusion in solids. The first one is interdiffusion, basically meaning the atoms of single materials are diffusing to another one. So you will see why we are talking about interdiffusion. And the self-diffusion is basically the atoms are migrating in a pure metal. So it's just moving around in its pure metal. Let's talk about first what is interdiffusion. Interdiffusion is simple. It's like we're mixing metal A and metal B. So this is metal A, let's say to the left hand side, and this is metal B to the right hand side. So you can think about many metals. For example, this is copper and this is zinc. This is copper, this is silver. We're having lots of mixtures of this kind of metals. And probably if you just simple imagine, if you just put some pure atoms on the left hand side and some pure atoms on the right hand side, they will start diffusing, right? They will not stay as that basically as your sugar meets your coffee, right? They will start diffusion to each other. The kind of motivation for that, driving force for that is completely on thermodynamics and completely on the second law of thermodynamics, because the whole world is tending to go to a chaos situation, and this is not chaos at all. So that's why we're trying to mix them. As I said, you will learn the motivation, and you will also learn an equation to describe that. That is mainly related to the entropy. So after certain diffusion, you will see, if we just characterize things via concentration, this term, concentration. So here, if you just don't diffuse, obviously the concentration for A is 100%. On the left-hand side, the concentration for B on the right-hand side is 100%. But due to the, let's say, nature of thermodynamics, our atoms are going to mix each other, and you see the concentration is basically kind of changing, from 100% to a, let's say, fine number for the atom A and for atom B, the same. And this is already giving you basically a kind of driving force for the interdiffusion, which is related to the concentration. And more specifically, it is related to the gradient of concentration. So gradient, basically, I think everybody knows what it is. It's dx, let's say it's d something. Let's say here is concentration. So d concentration over d position. So we call d position is dx. If this is the x axis, so dc over dx is the gradient of concentration. We will have a proper equation later on. And for the second type, which is the so-called self-diffusion, and this is defined as migration of host atoms in pure metals. So just look at this A, B, C, and D. So these are, let's say, a position of 4 atoms in initial state. And after a while, you will not find your A still being somewhere here, but your A will be basically moving to another place. And the same applies to B and C and D. So this is happening, this is happening in liquids, in gases. Everybody knows that. You have all this phenomena you see from daily life. But for solids, we don't realize that, because the solids basically they stay as it is. They don't move at all, right? But actually, if you just look into the solids, you will see they're not still. This is, once again, that's why I told you the mechanism about diffusion deep down is the same about solid and liquids. So the solid atoms are actually also vibrating, and they're also moving. You don't see them. They don't exhibit this phenomena in a massive manner. So macroscopically, you see your knife, kitchen knife is always as a knife. They're not transforming into something else. But let's say atomically, the atoms of iron, atoms of carbon, they're moving. They don't stay still as they are from one position from one time to another time. This is hard to imagine, but if you learn thermodynamics, you will know why. This is related to once again temperature. They only stay still. Maybe you can remember. They only stay still once you have absolute zero, temperature. Then everything will be staying nicely as they are. All right. So this is the second type of, let's say, diffusion, self-diffusion. And you probably were imagining, so A and B, they're just changing places. So they're changing like just magic. So they're switching places or what? So now I'm telling you why this is happening. So why the A atoms could go to various places. And the mechanism for that is about vacancy diffusion. So you probably remember we learned in our first week lecture, it's about the defects. We told you already. No solids is perfect, so almost nothing is perfect, and every solids there are defects, and defects are kind of classified into point, line, and phase. Maybe you remember all that. When we speak about point, because point defects, they are the basic unit of all the defects, and we have two types of points defects. Let me ask some of you. Maybe you still remember. Let me see. Arad. Oh, Arad it's just gone. I was looking at one name. Okay. Let me try to pick up some other people because I remember some of you are very active, which is excellent. Let me try to know also some others that I don't meet so often. For example, Hu. This is a complicated name. H-U-Y. How do you pronounce your name? Is it Hu?
It's Hui.
Hui. Oh, sorry, Hui. Yeah,
Yes.
Hui. Do you still remember what are the typical point defects?
I think there is a vacancy defect, and there is the one that there is an extra point in the lattice. I don't remember the name.
Excellent. Yeah, you're hitting it. That's right. So we have basically two types of point defense. One is vacancy, and that is very important, but you see it from the slide. That's right. And the second one is basically impurity, right? It's interstitial or substitial. So when you have something not as your own atom, you know, some foreign atoms are coming into your pure metal, they will be staying either a original place of your lattice, or they're staying at some, you know, gaps. So the first one is called substitial, and the second one is called interstitial. We're going to talk about basically three of them right now, because the vacancy diffusion and the substitution diffusion are just correlated with each other. Because basically we're talking about how to replace one lattice point to another. Yeah, and interstitial is something different. So excellent. Now, actually, I'm already displaying you a figure here. So this vacancy diffusion is explaining why we could have, let's say, the self-diffusion motivated, but it's not only related to self-diffusion, right? It is also related to, let's say, interdiffusion if we're talking about two very similar atoms, because the two similar atoms there, they can only replace one lattice point to another lattice point, and they're all driven by the vacancy diffusion. So how those kind of diffusion happening? Basically, you remember we have vacancies, and this is something unavoidable. And if you want to just trigger diffusion, if you want to make your atom moving from one place to another, what you're doing is actually in the following. So first, this atom is gonna switch places with the vacancy, and then this atom comes here, and the vacancy comes the initial place of the atom, and right after here, the vacancy could just switch place with another atom, and you see this atom is becoming here, and so on. So this is the mechanism basically for the interstitial or interdiffusion. Yeah, and the driving force is about, let's say, vacancy, and finally you can see this B atom could come into the A matrix. This is how the diffusion is happening. And you can see the diffusion rate. If we just look at this diffusion rate, we will give you a proper definition right away. But you can already imagine the diffusion rate is really depending on the number of vacancies. Remember the number of vacancies, what is deciding the number of vacancies, guys? Think about it. And the second is activation energy to exchange. So when you just swap a position with a vacancy and atom, you always need some energy to do this. Yeah, both of this are very much correlated to one thing. Yeah, we will know what that thing is right away. And the second mechanism is related to the second kind of defects, poor defects, that just who told us, that is the interstitial diffusion. And this is also related to the interstitial defects. Basically, that means if we have a small atoms, so we're mixing not copper and zinc, because copper, zinc, or copper, silver, they're really having very similar size of atoms. If we're mixing, let's say, copper with the carbon, so carbon is very small, or copper with hydrogen, so the smallest atoms. If you want to mix them together, the hydrogen will not be able to replace the lattice position of your copper. Basically, the carbon or hydrogen will be diffusing into the interstitial places. So like here or there, and they're just moving freely. So you could already imagine for such kind of diffusion, the speed is much more faster, right? Because you have basically unlimited, or not unlimited, at least the equivalent number of vacancies in terms of the interstitial positions as your atom number. All right, I think that's the two type of mechanism, and we could tell you what is the application. So what could we use for the diffusion? Yeah, and this is an example I already told you during the fatigue part. Maybe you don't remember. Because that is one way to improve your fatigue life. We said for fatigue life, we always want to protect our surfaces, and we want to kind of introduce a certain compressive stresses for our surfaces. And one way is so-called case hardening. So this is a typical procedure when you produce gears. Yeah. So when you have your gears produced by certain steel, you always put it into an oven, and the oven is basically containing carbon gas. And then you try to ask the carbon atoms basically diffuse into the surface of your steel, because this kind of diffusion of carbon will basically following the interstitial kind of diffusion way, right? And they will create basically two functions. The first one is something you remember, yeah? Because of the diffusion of these carbon atoms, you're kind of producing a compressive stresses into your original items, yeah, because you're pushing something into it, right? And this is already creating this so-called kind of compressive stresses. And the second point you will learn basically next week, because of this carbon, you're basically creating a certain solution. So I'm already giving you a term solution. Yeah, we will define that. What is a solution? You're creating a certain solution that is way stronger than the initial steel, than the initial iron, or than the initial steel you produced. And that is increasing the hardness of your steel, which is also good for the wear resistance. So two purposes of this kind of diffusion. All right, that was enough about definition, let's say mechanism and application. Now let's move to some quantitative measure about diffusion. So the first thing is about rate of diffusion. As you know, diffusion is a time-dependent process. We already spoke about it, either vacancy diffusion or interstitial diffusion. How do we measure diffusion? Yeah, this is one concept, and it is called flux, diffusion flux, so which is defined as J. I'm not sure if you have learned anything about flux. If you haven't, if this is the first time for you to meet flux, you just imagine it's a way of definition about, let's say, about speed. If we just speak about speed, it is some, it's about one item moving from one place to another place. So it's let's say the displacement over time, or d displacement over dt. That is speed. We're speaking about only one item. But for diffusion, we're not speaking about one item. So the speed of one atom does not make sense. It is a speed of a group of items. So the group of items basically are your group of your atoms, so the A or B. And for this case, we need to define not just the dt, we need to define an area. So we need to define a certain area when these atoms are moving. from one place to another. So that's why we're going to put an area here. So this is a flux, the definition flux. We will also learn about the heat flux later on. The philosophy is exactly the same. It's a certain time and a certain area. So you can see this is the unit of the flux. So kilogram over mass squared and over time, a second. Oh, not mass, sorry, it's meter squared. And how do we measure it? And this is also easy. So if you just have experiments to do, and when you just want to measure a diffusion rate in terms of diffusion flux, and if you just put a small sheet or membran, you will be able to measure the kind of diffused mass from one place to another, and then you can use the area and use the d mass over dt. Basically, you get your diffusion flux. So this is pretty simple, and the rest is getting a little bit hard, or harder and harder. But the requirement for you is not that high. So I think you will be able to understand it. You probably won't be able to derive anything of this, but you will be able to understand the equations. That's the most important criterion for now for you. The first thing we try to understand diffusion is simple. It's basically when you just mix A and B, basically you're mixing A and B, you want to know, what will be final, let's say, concentration. So initially you have 100% of A, 100% of B. So you have some sugar and you have your coffee. You want to mix your sugar into the coffee. And finally, you could calculate what is the concentration of your solution, right? Your coffee solution, a coffee sugar solution. That is easy because, finally, we're going to reach the equilibrium. All my sugar will diffuse into the coffee and I can calculate. But if I ask you at a certain time, at a certain position, when your sugar is not fully dissolved into your coffee, can you tell me what is the equation to describe that? What is the equation to describe at that time, at that position, what is the concentration of your sugar into your coffee? That is basically these two laws from Mr. Fick are trying to tell us. The first Fick's law is pretty easy because it is giving a very ideal case. The ideal case is something like we have a steady state diffusion. The steady state diffusion is defined like the rate of diffusion. So basically the flux is independent of time. So we don't consider time at all. Let's say we have concentration C1, we have concentration C2, let's say, of our solution here, and the C1 is diffusing into C2, and this kind of flux, so this is basically diffusion rate, right? This is the flux, is independent of time. So basically the C1 will be like C1 constantly, C2 will be like C2 constantly, and just infinitely they're diffusing. And most importantly, this line, they will stay as it is. They don't change according to time. If we have such a gradient in reality, eventually it's going to be like, let me get some pen, maybe that's easier. It's going to be like finally like this, right? Like equal. But here the basic assumption about steady state diffusion is this kind of diffusion flux is always like this, independent of time. It doesn't need to be a line, it could be something like this. This is possible. It could be nonlinear. The most important thing is this flux is independent of time. That's the key. And when we have such a situation, when it's a steady state diffusion, we could use this law, the Fick's first law, to describe it, because the flux basically is proportional to the gradient of concentration. So here it is. Maybe this is easier. You probably don't even need to think about it, right? If we don't think about time, what is the diffusion flux? What is the rate of diffusion? So because they're driven by concentration and it's proportional to dc over dx. All right. Yeah. So I think you can accept that. And it is proportional, of course. Then we define a term to describe it. This is so-called diffusion coefficient, and the diffusion direction or the flux direction is always opposite to the gradient one. That's why we gave a negative sign to the d. So this is basically the Fick's first law. Yeah, I think everybody got it. And if we just make it simple, if we make it the diffusion flux profile is like a line, as you can see here, and you could even approximate this equation like dc over dx is basically delta c over delta x. Yeah, basically at each position of this lines, they're equal, right? Yeah, because it's a linear profile. That's the steady state diffusion. And we spoke about steady state. Then there's non-steady state diffusion. Basically tells you what the flux will be dependent on, let's say, position and the time, right? And what does that mean? That means your concentration will be not independent of time. So for the steady state diffusion, the concentration, as I told you, is independent of time. So when your concentration is independent of time, so with the time, your concentration is moving. And how do we describe the diffusion? How do we describe the flux? Basically, how do I know at a certain position at a certain time of my coffee sugar solution, what is the concentration of that point? And here I'm giving you the Fick's second law. This is a little bit more complicated. As you can see, it describes the concentration rate. So the concentration over time, dc over dt is proportional to what? Is proportional to the second derivative of concentration over position. Yeah, so this is the key part. Yeah, you know, dc over dt is related to, if a quantity is related to the second derivative of something, it is a point that you are familiar with, right? You probably know acceleration. So the a is basically a second derivative of displacement over time. Yeah, but here we're talking about two dimension. So this is time and this is position. So this is a correlation between time and space. Yeah, this makes it a little bit harder for you to fully interpret. But we don't have time really to derive this equation for you. It is possible to derive it. You basically accept that. So the concentration change of your coffee and sugar solution over time, so the change over time is dependent on the second derivative, not the first derivative, but second derivative of the concentration gradient at that position. Try to get a sense of it. Maybe via the one equation I show you, you will get it better. As you can see, this is a differential equation, right? So this is something you have learned when you're just trying to do, let's say, some finite element method and so on. If you want to solve a differential equation, what you need basically is a boundary condition, right? So here, let me give you an example of boundary condition, a rather simple one. Consider a diffusion of copper into a bar of aluminum. So copper and aluminum. And how do we simplify that? We simplify that at the surface of this aluminum bar, the concentration of copper is a constant. So the constant, the concentration here do not change, meaning we have infinity amount of copper on the left-hand side. And the bar of the aluminum is also infinite. So it's infinitely long. And let's think about how would the diffusion look like in such a scenario. If we just describe that kind of boundary condition into equations, you probably could make the following. Let's say at the time zeros, at the beginning of this process, we know at the position x, at position, let's say 0, the concentration is C is equal to C0, right? So here is C0. And the affinity, or even for any position of the aluminum bar, it is also 0, right? And when we just try to, also C0, right? When we just try to have the diffusion at a certain time, you see the diffusion profile of copper into your aluminum is changing. So this is at the T0, and when it's T1, we know, right? When we have X equal to 0 at this position, the copper concentration is still CS, right? It's still CS. But when we just move a little bit into it, the concentration is decreasing. We don't know number, but when we just move to the infinity of our aluminum bar, we know the concentration of copper will be C0. Yeah. So that gives us basically 3 equations. So these are so-called boundary equations or boundary conditions. And with these 3 boundary conditions, and with those three kind of variables in your second Fick's law, you basically could finally derive an equation to understand your non-steady state diffusion. Yeah. So this is how the solution of second state, the non-steady state diffusion looks like. You basically could finally derive the concentration at a certain position and a certain time with respect to C0, CS, and position and time. So this is a so-called error function, which looks like this to be more specific. So you don't need to know the details. Basically, this full equation is giving you such a line, yeah, that you could really calculate at any position, like there, at any given time, what is the concentration. So this is the meaningful part of basically the solution to the Fick's second law. All right, so this is how it could be applied. I will not show you details here. You could just read on your own. And the last equation I want to share with you is related to the diffusion coefficient. So we talk about 2 equations about the flux, so diffusion flux, and both of these equations concerns one quantity. The quantity is so-called D, this diffusion coefficient. So what is decisive for diffusion coefficient? This is equation given here. So this is the equation which is looking similar to most of you, maybe, because this is the 3rd time for you to meet it. Yeah, maybe you remember the first time when we talked about vacancy. I guess exactly the same form of equation is deciding the volume fraction of your vacancy, and this is exactly the same deciding the diffusion rate. So you know there's a time factor and there's an energy factor. I will not emphasize in detail because you can really correlate it to the vacancy description very well. And you can also describe it in such a way. What I want to tell you is, maybe you remember when we just talk about the vacancy. When you add temperature at absolute 0, so when this term is 0, what does that tell you? It leads the D is becoming what, 0 as well. This is again confirming that when we have absolute 0 temperature, you will not have vacancy, you will not have diffusion. Yeah, even your interstitial positions will be still because all the atoms will be still. This is related to the second law of thermodynamics that you're going to learn most likely in your next semester or so. All right, and here is the final diagram I want to show you. And because we talk about interstitial diffusion, we talk about vacancy diffusion. Here I'm telling you what is difference. The difference is very huge. So look at it here. This is a carbon diffusion in a alpha iron. So this is just kind of iron, and this is basically interstitial diffusion. Yeah? If you just look at this red line, this is a aluminum in aluminum. This is basically vacancy diffusion. Yeah, this is certain temperature. And as you can see, for this temperature, we are having the diffusion coefficient difference like that. Yeah, so it doesn't appear too much different, but you can see actually the difference is several magnitudes. So the difference is actually huge between the interstitial and the cell. And we can see. Yeah. All right, a quick summary about diffusion. So basically, we told you what is diffusion and the definition about it. It's related to the mass transportation via atomic motion. And we learned basically two diffusion mechanisms, vacancy and interstitial. I think you got very good understanding about it. And we told you also three equations to describe the diffusion flux and also the diffusion coefficient. All right, I think that is the end about diffusion. And now, oh, it's almost 20. Now let's have a break before we move to the next subject, which is about phase diagram. This is something you are probably more familiar with. Guys, let's come back in about 7 minutes. Let's come back at 25 past 11, and we will continue with the phase diagram. All right. Go back to presentation mode. Okay, I hope everybody is back. And let's just continue. We said for the second part of today's lecture, we're going to speak about phase diagram and a small introduction about phase diagram. Basically, this is a diagram that tells you how many phases could be formed and what is the composition of each phase and what is the amount of each phase. So these are the guiding equations. Let's say I'm trying to emphasize here. You probably now don't still have a feeling about solid solution, or we're mixing solids with each other. So if you want to think about it, always take the example that we gave you at the beginning about sugar into coffee. Yeah, so the phase diagram of a sugar coffee, yeah, the sugar coffee phase diagram, yeah, you can put it that way, is basically trying to tell you, yeah, if you just mix your sugar into the coffee, how many phases will form? We don't have a very proper definition about phase, but you have a feeling in your mind. Stick to that. I just want to tell you, most likely you want to achieve a uniform solution. So solution again, right? You want your sugar dissolved into the coffee uniformly. But maybe you try to do this experiments at home. Probably you did it in the past. You just continue to put your sugar into your coffee. When you just put more and more, there's one limit. You know, you cannot dissolve your sugar into the coffee anymore. You will have your, let's say, sugar coffee solution, yeah, which is uniform, and you will have some sugar, yeah, sugar as the sugar in your package, and they will not dissolve anymore. So you in that case, basically, we're talking about two phases. So the first phase is coffee sugar solution, and the second one is sugar as a solid phase, right? So that is two phases. And you want to know for my coffee sugar solution, so what is the concentration of that? What is the composition? And that's the second point. And you also want to know how much your sugar coffee solution is, how much your sugar is, because then you could know, I want to dissolve the most amount of sugar into my coffee, but I don't want to waste my sugar. I want to just know that amount, and then I can always, you know, put the right amount of coffee next time. So basically, these are the idea for us, you know, to form this phase diagram. So we want to have a diagram that we could know, yeah, at a certain, let's say, amount or certain temperature, certain composition, we know how many phases we're going to form, and for that phase, how much we have it, what is the composition, and what is the amount. So maybe that helps you understand it better. That also brings us to the learning objectives for today. So the first one is going to be, we try to schematically sketch you the isomorphous and eutectic phase diagrams. So don't be surprised by these two terms. You will learn them later. And the second, so there are really a lot. This is probably the course that you learned the new terms the most. But they're very easy to understand. I will tell you very soon. And the second point is about gave you a binary phase diagram that determines the phase composition and mass fraction of each phase, exactly as what I told you. And then you could also have a binary phase diagram, which is a little bit more complicated. And you could locate all this eutectic, eutectoid, peritectic, and congruent phases. And you will be able to write the transformation equations for them or transformation reactions for them. And the last point is a composition, is a very famous phase diagram. It is called iron carbon phase diagram or a iron carbon alloy. So this is nothing but steel, basically. So if you just talk to a very small kid, when you just ask, what is a knife made? They probably will answer you, this is made of iron, because this is what they learn from high school or preliminary school and so on. But after certain training, you know, no, that's not iron, that is steel. So what is the difference between iron and steel? Probably you know, steel is an alloy. So a more advanced name for steel is iron carbon alloy. So if you just say, I'm going to use my iron carbon alloy made knife to cook my dinner tonight, then you're becoming a material science engineering expert. And for this diagram, you're going to really learn in detail about it, and you will be able to specify this hypoeutectoid and hypereutectoid points, and you'll be able to calculate the mass fraction about proeutectoid fraction and pearlite, and also make finally a microstructure prediction during the phase transformation. All right, that is basically all about it. And now let's just move slide by slide. First, I would like to give you a very simple, the simplest phase diagram, which is called a unary phase diagram. So basically, we're talking about just one component. So here the component is water. So we know the water changes its phases, you know, from, let's say, solid ice to liquid water, and finally vapor. And the changes just happen with respect to temperature. So everybody is familiar with 0 and 100 degrees C, and that is the phase changing point for water. And we're actually speaking about 1 atm, because this is our ambient pressure. But you probably should know, the temperature for the phase transformation of water or ice or vapor is not constant, right? When you just have a high pressure, maybe you know the high pressure cooker. So basically, why that could give you a very fast way to cook your food, because you can get your water temperature or your cooker temperature higher than 100 degrees C. That is temperature we could only reach with the normal pressure. When you just have a higher pressure, you could get 120 or even 200. That will make your food really, fastly cook. And that is the unary phase diagram. So you know something about that. And now we're going to speak about finally binary phase diagram. So what is binary phase diagram? Meaning we're talking about two things. So A and B. So like sugar and coffee, or copper and zinc. So this is the main topic we're going to discuss for our case. So there are some definition, but first let's talk about this diagram here. So once again, so here's water and sugar, but you can just imagine this coffee and sugar, or sugar and some liquid, something, yeah. And you know, as I already asked you, let's say we talk about the room temperature, something like 20 degrees C. You can just dissolve your sugar into your water or coffee, yeah, uniformly. So then you form a uniform solution, and in a certain case, in a certain limit. So as you can see, this kind of line here is indicating when you just put your sugar more than 60 something percent, you will not be able to form a uniform solution, and you will basically form another phase. This is the liquid, so the solution of your sugar coffee, and with the sugar itself. So meaning the sugar will not dissolve anymore. So it's becoming two phases. So that is basically the kind of idea for us to define something. So the first definition is about solution. So solution means solid, liquid, or gas solutions that is forming a single phase. So here everything is uniform, right? But when you just kind of go beyond this line is so-called the solubility limit. Meaning when you just go beyond this line, your sugar will not be able to dissolve into your coffee anymore. And these two things, they're so-called mixture. So basically, this is a mixture of more than one phase, because here we have two phases, but they're still together. They're still one piece, but this is a so-called mixture. And that is the important part. So that's the question I would like to ask you. But what you could get is from this diagram, you're able to read what is the solubility of sugar into your coffee at room temperature. So now you know, when I want to just have the maximum sugar possible, I shouldn't put the weight of my sugar more than 65% of the water. Here it's not coffee, unfortunately, of water. But you say, oh, I just love sugar, I want to get more. So how do you do it? Then we just increase temperature, right? When you just have higher temperature of your coffee, you will be able to dissolve more sugar into it, right? So this is already a good use of a phase diagram. So we're still speaking about a very simple case, sugar and water. Now we're gonna speak a little bit more complicated case. So this is exactly what I already told you. So here I'm trying to give you some animation here. So a more complicated case is we're speaking about two solids. So zinc and copper, or aluminum and copper. And here we're firstly giving you a proper definition about components. So components, basically the elements that we're trying to mix with. So here we're talking about zinc, aluminum, and copper. And finally, I'm giving you a proper definition of phase. So the definition of phase is very similar to the definition of failure. Maybe you still remember. So we don't define from a structure level or from a kind of in-depth level of this thing. We're defining actually from its exterior behavior. So phase is defined a region, a volume, an area, whatever of your material that behaves equivalent physical and chemical properties. So this is exactly this definition is giving you. So when we speak about one phase, we're speaking about this region of material are behaving uniformly the same in terms of their physical property or chemical properties. I think everybody has it in mind. This is just a proper definition for you to think about. Oh, this is one phase or two phases. Now you should think about, oh, are they behaving exactly the same uniformly? Okay, yes, then they're the one phase. If not, there are two phases. So here I'm already giving you two phases of this aluminum copper line. So you see, obviously already optically from the micrograph, we have two phases. So there's the beta phase, the lighter one, and also the alpha phase, the darker one. We will right away talk about this phase diagram about aluminum and copper. You will know what is alpha and what is beta. There's just one thing. We talk about solubility for, sugar into water or sugar into coffee. Actually, there's also solubility when we just try to mix the solids. Yeah. What is the solubility? What is defining the solubility about solids? So first, if we talk about nickel and copper, yeah, the kind of solid solubility is deciding by their crystal structure and their electronegatividity, and also the kind of radius of the atom. So if we're having very similar kind of composition or structures of these two components, nickel and copper, basically nickel and copper can kind of dissolve each other 100%. So you will always be able to form a solid solution, for nickel and copper. Yeah. So either 100% nickel or 100% copper, or any combination in between. So this is so-called totally soluble. And this is very rare, to be honest. This is very rare. And it can only happen for a few atoms. We will show you right away. So this is another kind of still the same. So nickel and copper diagram. And this is how it looks like. So here we are speaking about a series phase diagram finally. You see already two unary and binary phase diagram basically for temperature and pressure. But here we are actually kicking the pressure off, because we don't need pressure anymore. Usually we always do everything, let's say at 1 atm. So about our ambient pressure. So we don't talk about pressure anymore. So this is a common, let's say, binary phase diagram we're talking about. The x-axis is basically telling you what is the composition. So here is 0, meaning we have pure copper and 0 nickel. And here's 100, means we have 100% of nickel and no copper anymore. By the way, the unit is here, pay attention, is a weight percentage. Yeah, this is important. And the y-axis is so-called temperature. Yeah, maybe you're wondering why. Yeah, so you can also just vice versa, put the temperature on the x-axis. But as I told you, why we were learning diffusion, why we're learning phase diagram, why we're learning phase transformation. The reason for that is completely related what we're going to learn about processes. Yeah, because when you want to make your engineering materials, as we discussed at the very beginning, you need to do a very necessary operation, which is so-called solidification. Yeah, this is a step that is not possible to be avoided. And you want to know what is happening to your material during solidification. Yeah, or during, let's say, even more general, the decrease of temperature. Many things are happening, to be honest. This is something I have to tell you. That's why we're studying all this, because this diagram basically is telling you, when you just go from, let's say, 500 degrees C back to room temperature, what is changing in your material? Yeah, this is the key. And the changing of material is driven by phase, phase changes, phase transformation. And the mechanism about phase transformation, change of phases, is by diffusion. So that's why we're on learning about this. And so here, I'm basically telling you this is the phase diagram, so temperature and composition. How to read this diagram, always think about the process. So think about you're cooling down something or you are heating up something. And what is the change when I just do this in terms of the composition and phases. So for this kind of copper and nickel system, as I told you, these two phases can basically just dissolve each other completely. That's why we could have, for example, here, we have the liquid and into a certain region. So at a certain temperature field, we will have a kind of combination, a mixture about liquid and solid. Yeah, so this is happening. I mean, they're completely dissolve each other, but at a certain time, at a certain temperature, you could still have a mixture. But if you just cool a little bit down, then you would have a 100% solution. Yeah. So that's why in this phase diagram, you would find basically 3 phases. So one is liquid, and then is liquid plus a solid, and then it's becoming solid completely. Yeah. And if you just recall what we had with the sugar coffee situation, actually we're displaying you only the liquid, yeah, and the coffee plus sugar part. So that is the solid plus a liquid. And actually, if you just decrease temperature, you will have 100% of solid. Just to give you 2 definitions, this line that is distinguishing the completely liquid phase to a mixture is so-called liquidus line. And the other line is distinguishing a phase of completely solid with a mixture is called solidus line. So this is important. So keep it in mind. And with this kind of knowledge learned, basically, you would be able to understand this diagram better. So now I show you some application of this diagram. And this diagram basically is so-called isomorphous diagram, meaning we could have completely solubility about one component to another, yeah, in a solid phase. Yeah, this is the important part. In a solid phase, we could have completely a one phase. This is so-called isomorphous binary phase diagram. And right away, we're going to move to a use of this phase diagram. So we've said we want to give you this tool to be able to determine something. And here I'm going to show you 3 kind of application of the phase diagram. So the first application of phase diagram is to determine what phases are present. This is actually very, very simple thing. I will just give you some example. So let me ask you. So when we have a certain temperature and a certain composition of copper and nickel, you want to know what should be the phase over there. And from this diagram, you could see, okay, if it's 1160% of nickel, it is solid solution. And if it's 1250 degrees C and 30% of nickel, it's a mixture. And of course, okay, I don't have the third example, but if it's higher, you have a liquid. That was easy. And the second application of phase diagram is so-called phase to determine the phase composition. Yeah, this is especially useful when you are having a mixture condition. For example, here we have that is the easy part. Yeah, when we have 30% of nickel and with a high temperature, that is completely liquid. When it's lower temperature, it's solid. But when we have a mixture, so when we have the situation about 1250 degrees C, we have both alpha and liquid present. And we want to know what kind of liquid solution we have and what kind of solid solution we have. So with this diagram, you could just use a so-called tie line. Basically, you located this composition and you locate this temperature, you make a line to touch your liquid use line and to touch your solid use line, then you know exactly. So the mixture at this temperature and composition is composed of, a liquid solution with here 32% of nickel and a solid solution of 43% of nickel. So this is the point. And you can use it to determine finally, oh, the solution, the mixture contains of these 2 solutions. And the third one is more quantitative, because okay, I have combination of 2 solutions, the liquid and solid. And I want to know how much is the solid solution and how much is liquid solution. Yeah. And here this is the third application of the phase diagram, which is so-called the lever rule. Actually, this is pretty simple for you to imagine, because basically we are having this 2, oh, just 1 second, guys, excuse me. All right, so I'm back. You know, for these two kind of solid solutions, actually we're reaching the same goal. We're reaching the same balance, which is we're going to finally contain, let's say, this 35% of nickel into the whole solution. Yeah, that's why how these two kind of solutions should be composed of and what is the composition or fraction of it. Basically, they should follow this so-called lever rule. Basically, you know, yeah, this equation. So the amount of this alpha, so the solid phase, times this kind of fraction or this kind of length should be equal to the amount of liquidus, so the liquid solution times this distance, right? And we know here should be 35%. That gives you a simple equation just following that. Basically, if we want to get the volume fraction of the liquid solution, basically we use the S, so the longer distance divided by R plus S, the whole distance, we know the concentration of it. And if you want to calculate the volume fraction of the solid, we're using the R, the short part, and divide by the length of it. Yeah. So meaning when we have more, let's say, nickel in your composition, the weight of it is less. When you have less nickel into your solution, the weight of it is higher. Everybody got it, right? Then you get an average exactly at 35%. All right. So that's the third and actually the most important application of the phase diagram. Because with this phase diagram, you can finally calculate how much kind of solid is there, how much liquid is there. Okay, and this is a example for you to calculate. You will be able to practice on your own later. So here finally we get a 73% of the liquid and 27% of the solid. All right. And now I want to give you a little bit process of it. So we know already three most important applications. We said the phase diagram is finally basically to let you know how the microstructure is produced, because our materials always go from the high temperature to low temperature. Here I'm already giving you a little sketch of it. So let's say we have a certain liquid solution of copper and nickel alloy. So no matter how they're produced, you kind of get such a situation over there. And now you finally want to produce your tool. And you want to produce a tool made of nickel and copper. So you start from the liquid phase and you try to, right? You try to solidify it. You try to decrease your temperature. And what is happening in your solution, liquid solution, is that you have 35% of liquid, 35% of nickel, sorry, of nickel liquid solution. And when you just hit the solidus line, the liquidus line, you know, you start to get a mixture. So the mixture is composed of a certain amount of liquid solution. Let's say we just hit the position of the liquidus line. You will have the 35% of your liquid solution plus a very high number of your solid. So this is a 46% of nickel. Yeah, meaning you have a liquid solution with 35% of nickel, and then you have some small points. Yeah, they're so-called nucleates. We will learn that during the process. And they're solids, and this kind of nucleus, this kind of solid points contain 46% of nickel. Yeah, remember that. But you know, you try to reduce your temperature further. So we're here talking about always hitting a, let's say, a equivalent phase. So you're always waiting for your whole system becoming equilibrium. Yeah, that's why when you just decrease to the point C, actually at this time, yeah, you have to forget about the previous time. at this time, your mixture is looking like this. You have, let's say, more solid solution, and you have less liquid solution. And more importantly, the composition of your liquid solution is becoming nickel less. It contains only 32% of nickel. And in your solid, the concentration of nickel is also becoming less. Right? It's becoming from 46 to 43. Yeah, but the weight of the solid solution is becoming much higher. Yeah, so the composition is completely different. You have to keep in mind the composition is not constant. The composition of these two phases are completely different. And finally, you reach this solidus line. And here you see you have the 36% of nickel. Yeah, it's almost on the solidus line, right? So your kind of system is almost a uniform phase again. It's just a little bit mixture there. And you have a 24% of nickel liquid solution into your phase. And if you just decrease your temperature further, you become 100% solid phase, and it's uniform, and it's 100%, 35% of nickel. All right. So I hope you could understand this phase, because this is the simplest. And try to rehearse it in your mind, what is the microstructure doing and how this is driving. You know, the mechanism that makes this change happening is basically driven by diffusion. You probably could already remember that. And that is a equilibrium structure. So, you know, we have the uniform case from one to the other. But, you know, in very often cases, we don't have equilibrium. We always have a fast cooling. So we don't wait our structure to become into equilibrium. And that's why actually you will have, when you have a small nuclei, you have very high percent of nickel into it. And when you just try to grow your kind of solid phase bigger and bigger, and the nickel concentration becoming less and less, right? And you can imagine when you finally reach your 100% of solid, this outer layer will contain nickel with a solution less than 35%, right? Because if it's uniform, it's 35%. But if you have this kind of layered structure, because at the center you have higher concentration than the outer layer, that means your outer layer will have to be less than 35%. Okay, so that is a situation which is more close to reality, actually. And this is really ideal when you have completely uniform. All right, I think we're at the right time at the moment to stop today's lecture. I will not go to the second important phase diagram to talk about today, but would rather leave it to tomorrow. Yeah. All right, I think we can stop right here. If you have any questions, we can leave it now. Otherwise, we are done for today.